Swayam Prabha. Digital India. Educated India.
Good morning and welcome to the lecture 44 of module 9, which is on electrophoretic and electroless deposition process. So this is another, these are two similar but not exactly the same type of coating methods, but is fairly different in terms of mechanism from electrodeposition or electroplating. In fact, we'll see that in this two methods, though we form deposits without or with the application of electrical current, no electrical current, but there could be two electrodes in which the ions get deposited, but there is no complete circuit. There's no total closed circuit situation like in case of electrodeposition, where the cations move from anode to cathode and anions move from cathode to anode and gets deposited, and outside the circuit we see electronic conduction, and inside the bath we see electrolytic conduction, so a complete circuit. In contrast to that, in these two processes of electrophoretic and electroless deposition, we'll see no such complete electrical cycle or circuit. So just imagine, this is just to show you that when failures occur, typically say in printed circuit boards, due to the presence of aggressive molecules or ions like hydrogen sulfide or presence of humidity, it actually causes enormous amount of damage, and in fact, in order to prevent such damage happening in the circuit boards like here or here, we generally try to create a deposit which gives cathodic protection through the so-called electroless nickel immersion gold coated copper component. So electroless nickel immersion gold NIC coating on copper component, and this gives the so-called cathodic protection. These are the corrosion products, and if you do spectroscopic analysis, then you realize that apart from the metal values, we also have presence of sulfur or oxygen ions, which means that the corrosion happened because of reaction between the hydrogen sulfide and maybe water molecules. So the first method that we are going to discuss is the so-called electrophoretic deposition. So unlike electroplating or electrodeposition, here the species which gets deposited is not an ion but a particle. So essentially a neutral particle and not even a neutral atom. So a particle, but of course it can carry certain surface charge. So the typical applications could be, for example, to create functionally graded materials, to give, let's say, combination of wear and corrosion resistance or conductivity and wear resistance and so on. It has applications in laminated materials, maybe polymeric, maybe non-metallic. Also, the most important thing is that there are very many applications related to near shape fabrication of complex shaped glasses and ceramics as foils, also as complex shapes. Then fabrication of solid oxide fuel cell, where you'd like to create the anodes and cathodes with certain deposition of ions or neutrals with for maintaining certain composition. The typical process parameters will be of course the concentration of solutes that we have in the suspension, the viscosity of the suspension, the zeta potential, which actually will control the rate at which the deposition occurs, the dielectric constant of the liquid, the voltage that we apply, the deposition time, the length of the deposition time, size and shape of the solid, substrates on which deposition is happening, and of course conductivity of the suspension. One of the biggest advantage in these two, electrophoretic or electroless deposition, is the fact that the electrodes can be even non-conducting material, or in other words, we actually can cause deposition or allow deposition on non-conducting surfaces. So we already mentioned that the particle size, dielectric constant, conductivity of suspension, and viscosity, these are the four major variables. So essentially we are talking about a particle with certain surface charge, and these particles, what we understand is that as we go away from the, so if this is the center, so this is the center, as we move away from center to the periphery, then or we actually start from the surface of the particle. So this is surface charge. So this is the particle that we are going to deposit, and these are surface charges. So if we start measuring from the surface, and if this is where the surface coincides, so along the distance away from the surface, the charge density decreases. And so this is typically because of the fact that the attachment of the charged particles to the surface is the maximum, the density is the highest. So this is actually expressed in terms of the zeta potential, which is the electrical potential at the interfacial double layer, and is equal to the potential difference between the dispersion medium and stationary fluid around the dispersoid. So this is the fluid, and we have these ions floating around. So the potential difference between the dispersion medium and the stationary fluid around the dispersoid, so these are the dispersoids. It helps in stabilizing the suspension, determine direction and velocity of particles, and grain density of deposit. So we are not depositing these ions, we are depositing this particle, which is a neutral particle. But the particle acquires surface charges and hence an electrical character. When we apply certain potential difference, so or because of the natural potential difference created because of charge accumulation on this and some other parts which has less charge. So because of this reason, the electrical potential difference, these particles get deposited. So what we deposit are not the ions but these particles. And typically they are maintained, these particles are maintained in colloidal form. So basically they can be, unlike aqueous solution, we possibly can use some non-polar, even polymeric solutions in which these particles can be suspended as a colloidal suspension. So both the thickness of the deposit or the mass of the deposit, they are proportional to the time and also to the applied voltage. So with more time or more applied voltage, the thickness and the total deposit amount, both of them should increase. And one can refer to these two particular published literature to get further details of this. And by the way, this is deposition of zinc oxide in this case, and this is hydroxyapatite deposition in this case. And this is also interesting because hydroxyapatite is basically a phosphate salt which is neutral, but you can deposit this on titanium 6 aluminum vanadium, which is a standard material for various orthopedic implant applications. And if you want to make the surface more bioactive or more conducive for cell integration or tissue integration, then you would like to coat a typical metallic surface with such bioactive coating, and but then they are neutral, they are not charged particles, they are not ions, and yet you can deposit on a metallic surface by way of this electrophoretic deposition. Whereas for creation of electrodes, particularly say solid oxide fuel cell or some other sensor or semiconducting applications, solar cell fabrication, one can deposit zinc oxide by electrophoretic deposition on a metallic or a non-metallic substrate. So as I said that in electrodeposition, you are dealing with ions, and the cations get reduced at the cathode and gets deposited as adatoms, and the conductance of the liquid is requirement is high, or in other words, the electrolytic solution that we actually use has to be necessarily able to conduct cations and anions, and the bath is usually aqueous in nature. In contrast, for electrophoretic deposition, we are talking about solid particles of certain diameter, usually very ultrafine particles. There is no charge transfer involved, though we have a surface charge layer, but those are not part of the deposition process. The medium can be not completely insulating, but may have low conductivity. And instead of water, we can use organic medium or polymeric medium, or typically a dispersion. So the deposition, the electrophoretic deposition can be cathodic or anodic. So in this case, so when we have a dispersion in a medium, so cathodic electrophoretic dispersion refers to a process where deposition occurs on the cathode by positively charged particles. So these are positively charged particles, and typically if you have a cathode, then they get deposited here. So when I say deposited on cathode, what I mean is that these particles are surrounded by charge which is positive in nature, and hence they get deposited onto the cathode or the negative electrode. On the other hand, we can have a situation where particles which have acquired negative surface charge may get deposited on the positive electrode, the anode, and hence we call that anodic electrophoretic deposition. So typical advantage is that we actually can get fairly uniform coating without porosity. It can deposit on complex contours and shapes and sizes. There could be fairly fast coating rate. Can maintain very high purity. We actually can use a wide range of materials, conducting metals, ceramics, oxides, polymers, so all kinds of materials. The compositional control is easy, and the process can be automated and precise, but of course not as precise as electrolytic deposition or electroplating. Usually it's an environment-friendly process, unlike those conversion coating processes where you may have to be dealing with phosphate ions or hexavalent chromium ions. The process is generally economic, and the energy consumption also is very low. So the electroless plating also is called chemical plating or autocatalytic plating, because you're not applying electrical potential difference, and yet particles, neutral particles having acquired charge on the surface is getting deposited onto a particular surface, and that surface can be conducting or non-conducting surface, but usually the medium is a liquid bath. So we use it, or we are interested because of decorative purpose, also prevention of wear, corrosion, or other surface degradations. And what we coat basically are the grains or individual particles, powder in nature, usually very, very small size. One can actually create composite coatings, not just alloy, but even composite coatings with dissimilar materials by suspending suitable powders in the bath. So there are two main types of electroless deposition. One is the so-called through displacement deposition or immersion plating. Another is the autocatalytic deposition, which is what we are discussing now. The main advantage is that the thickness we already discussed is fairly uniform. We can deposit on all kinds of materials, conducting, non-conducting. We can choose any complex shape, and there is no electrical current flow, be it in continuous flow or in pulse mode. There is no such requirement. So essentially, we are talking about presence of metal ions acquiring certain charge. Now we are going into the other methods where So we already said this is unlike electrophoretic. When we move to electroless, then here we are talking about these kind of processes where the process is autocatalytic in nature. That means there is some displacement reaction happening and the deposition of uniform coating on even conducting or non-conducting surfaces. So this so-called electroless or autocatalytic process will require the ions. Here we are not talking about particles, neutral particles. Here we are talking about actually ions. So the ions actually carry some reduction, are dispersed in some reduction solution, and so when the ions actually are in contact with a reducing agent, then the reduction reactions takes place. That means these positively charged ions get reduced into neutral atoms, and these atoms get deposited onto the surface. So this is the deposited created by so-called autocatalytic process. The presence of the reducing agent is very important because this reducing agent is responsible for the reduction reaction, because of which such deposition takes place. If you compare electroplating, electroless deposition and immersion deposition, which is what we are going to discuss at the end, but we are not considering electrophoretic deposition here. So as we can see that in immersion deposition, the rate is slowest and it tapers off. In electroless deposition, we can maintain a fair amount of linearity until certain period of time, and so thickness as a function of time is small and tapers off or plateaus off in case of immersion deposition, is of lower rate but fairly linear in case of electroless deposition, and in case of electroplating, of course, this can be with a much steeper slope, or the amount of deposition, rate of deposition could be higher. So these are the examples of electroless deposition. Let's say with copper, this is with silver, this is with nickel or nickel phosphide or nickel phosphorus, or this is for cobalt or silver, and this is for copper or gold or copper. So in all the cases, the reducing agent that we use are different. You see formaldehyde in case of copper, again formaldehyde in case of silver, but hypophosphite in case of nickel phosphorus, hydrazine in case of cobalt or silver, ascorbic acid in case of copper or gold. So the reactions look somewhat like that. And what we see is in all the cases, the neutral atoms are getting deposited, and this is through a so-called autocatalytic reduction process. So the bath will contain the ions of interest, say for example nickel, and is added as a chloride salt. The electrolyte is conductive in nature, one of these electrolytes. We also use complexants, reducing agents. This is very important for the deposition to occur, reduction reaction to take place. And we also use additives for maintaining surface topography or avoid impurities or improve the nucleation rates and so on. So we have already talked about some of the reducing agents here, for example, hypophosphite, hydrazine, ascorbic acid. So formaldehyde is another very standard reducing agent, hypophosphorus acid or hypophosphite, borohydrides, diborans. These are standard reducing agents. The metals which actually are suitable for electroless deposition, that means in this kind of an autocatalytic displacive reaction, is copper, nickel phosphorus. This is one of the limitations, that we don't have as many choices as we had in case of electrolytic deposition or electroplating. Here generally one talks about nickel is the most prevalent, most widely used, nickel phosphorus, or copper or nickel phosphorus silicon carbide particles together. So then what happens? So typically at the cathodic site, this is the deposition process we are talking about. So we have nickel ions in the solution, and there is a reductive process involved, and this reduction reaction is possible because we actually provide this reducing agent coming as these orthophosphide ions, hypophosphite ions. So hypophosphite that actually acquires, that liberates electrons, and these electrons are used. So hypophosphite compound in aqueous solution liberates electrons. These electrons combines with nickel ions and produces nickel deposits at the cathode. So this is the deposition process, but there is no current flow. There is no closed electrical circuit available. Now, and in the process, of course, it evolves hydrogen. So the overall reaction is this, that I have nickel ions available in the solution, and I allow hypophosphite, I probably am using an hypophosphite solution in aqueous medium, and I produce orthophosphide ion, and the electrons that I donate from this anodic reaction is used up to reduce nickel cation into nickel deposits. So this reaction is spontaneous when we have a negative value of the Gibbs energy change. So typical applications could be on computer memory disks, so nickel coating on them for wear and corrosion resistance, automotive parts, electronic items, oil and chemical machineries or components, various printing jobs, food items or food containers, aerospace components, machineries, and so on. So these are listed in details here, sensors, valves, molds for producing plastic and glass components, gears, crankshafts, magnetic tapes, on aluminum, corrosion-resistant coatings in saline environments, and also plating on plastics. And this is where electrolysis deposition scores a major advantage over electrolytic deposition, that by this kind of an electrolysis process, and like we said also in case of electrophoretic process, we can deposit a species on non-conducting surface like plastics. One more important thing to remember is that electrophoretic does not use ions, but electroless, or one other type we are going to soon discuss is through a displacive reaction. There also we will see that ions are involved, but not neutrals. So electroless deposition of nickel phosphorus, nickel boron, or nickel phosphorus boron on aluminum, these are the examples, and in all these cases, if you do a nano indentation, then you see that there is a certain amount of linearity in these curves, and from the linear portions you can measure the elastic modulus. So you can show actually that the mechanical property of these deposits is very good, and that's why one goes for this nickel phosphorus and nickel boron coatings. And if there is a very high modulus coating possible, thin coating on the surface, then obviously the wear rate improves even at higher load. So you are able to maintain fairly high amount of wear resistance at even loads of say up to about 3, 4, 5 newtons. So we actually need an autocatalytic substrate to allow deposition to initiate and continue. The deposition rate can be fairly smooth and constant. We can create uniform thickness of the deposit. The bath has to be controlled properly to maintain the same amount of deposit thickness and composition. and the bath usually has a certain lifetime. So otherwise, unless you replenish, then the deposit thickness reduces and also the uniformity is lost. So this is another form of electroless deposition. In fact, it's called immersion deposition, where we are talking about, so this is a slightly different process. So first of all, there is a there's a spontaneous displacement reaction, and this means that for example, if I have iron and copper, so iron will get oxidized and contribute iron ions to the solution. Okay, and if this is connected to the other part of the system by some conduction path, so that the electrons liberated, so when iron gets oxidized, the electrons get liberated and flow into the other side. And now in the solution, if you also have copper ions available, so the electrons are acquired through this electrode at the cathode side. So this is the negative electrode and this is the positive electrode. And so these ions, these electrons basically help in neutralizing these copper ions at the surface of this electrode, so that copper gets deposited onto copper. I'm not applying any separate electrode potential, separate electrical potential difference. I'm not allowing any current. I'm not applying any impressed current, but because of spontaneous displacement reaction, iron is getting oxidized, contributing electrons which flows through the outer circuit, and this copper electrode acquires the character of a cathode because of the flow of negative charges, and those negative charges combine with the copper ions available in the solution and allows deposition of copper on copper. So this is the so-called immersion deposition, okay, which is essentially a displacement deposition process. So this is the reaction typically one sees at the cathode, and this is what we see at the anode, and the overall reaction will be like this. So there are various couples actually which is possible for such deposition process. There are certain limitations. For example, the control, the rate of deposition is not very easy to control. The deposit may be porous and poorly adherent. The rate declines with time because the supply of ions decrease, and ceases when steel surface is completely, or the iron surface is completely covered with copper. So hence electroless deposition of metal is more favorable than this immersion deposition, but the surface needs to be catalytically activated for the metal to be deposited. On the other hand, the electrolytic bath that we use in case of immersion deposition should actually provide an electrolyte to conduct the electricity, or the ionic conduction, should actually be should provide the source of metal to be plated, which say copper or nickel, whatever we are dissolving and depositing. We require a reducing agent to reduce the metal ion to metal at the cathode, and it should also be able to wet the cathode by allowing good adhesion between the cathode and the deposit, and also it should help to stabilize the temperature by some amount of circulation. So we need to ask ourselves, what is electrophoretic deposition? We have to remember that here we are talking about neutrals, which actually particles which can acquire some charge onto the surface, positive or negative. And then what is the electroless deposition? How does it vary? Here we are talking about ions and not neutrals. What is the difference between electrodeposition and electroless deposition? Why do we call it electroless deposition? What are the special features of electroless deposition? What factors affect the electroless plating or deposition? what are the attractive properties or possibilities for electroless coatings? How versatile it is compared to electrolytic deposition, or does it have any limitations? What is immersion deposition? Is it an electroless deposition or it is an electrolytic deposition? Why do we call it a displacement, spontaneous displacement reaction? And how does it compare with electroless deposition or the autocatalytic deposition? So, with this, we'll stop here now for the time being. Thank you very much.